In this video, I'm going to present the project for ECE 596C at University of Victoria, which is simulation and visualization for NBody problem. The NBody problem is a problem of predicting the individual motions of a group of objects interacting with each other. The solution for one-body problem is trivial, and the two-body problem can be solved using Kepler's laws of planetary motion. But for problems involving more bodies, the solutions are either too complex or no known solutions exist. Therefore, such problems are solved and simulated using computational methods. In this project, a software is built to simulate the embodied problem and visualize the result. This software contains 4 modules. The math module provides basic data classes and functions for simulation and visualization. The configuration module parses command line options. The simulation module provides functionality for embodied simulation, and the visualization module provides functionality for visualizing simulation results. The simulation module consists of 5 components. The first component, gravity solver, computes gravitational force and acceleration on each body. For a small number of bodies, the problem can be solved using the direct algorithm. This brute algorithm involves computing the gravitational forces influenced by all other bodies for each body. When the number of bodies is large, the brute direct algorithm makes the calculation especially time-consuming. An approximate method called Barnes-Hart algorithm is used to reduce the time complexity. In Barnes-Hart algorithm, the space is recursively subdivided into subcells via an OC tree. Only bodies from nearby cells need to be treated individually. Bodies in distant cells can be treated as a single large body centered at the cell center of mass. The second component, integrator, involves bodies forward one time step at a time. Currently, only leapfrog algorithm is supported. The leapfrog algorithm has 3 stages. In the first stage, the position is advanced for half a time step while keeping the velocity fixed. In the second stage, the velocity is advanced for one time step while keeping the position fixed. In the third stage, the position is again advanced for half a time step using new velocity. The third component, boundary condition handler, determines how to deal with bodies when they reach the boundary. By default, there are no boundaries, so bodies can have arbitrary coordinates in 3D space. Under open boundary condition, bodies will be removed if they cross the boundary. When rebound boundary condition are selected, bodies will rebound when colliding with the boundary box. When periodic boundary conditions are used, the bodies will be reinserted on the opposite side if they cross the boundary. The first component, collision detector, checks for physical collisions between bodies. By default, collisions are not detected. In this case, the bodies will just pass through each other. The direct and OC tree methods are similar to algorithms used in gravity solver. The direct method simply checks the overlaps between every body pair, and the OC tree method only checks nearby bodies via an OC tree. The last component is collision resolver. It determines how to resolve the collision. The hard collision resolver assumes hard sphere collision. It conserves momentum, mass, and the kinetic energy depending on the coefficient of restitution. The merge collision resolver merges 2 collided bodies. It conserves momentum, mass, volume, but not kinetic energy. Most computation in the embodied simulation can be parallelized. Here are the statistics of time spent simulating 1,000 and 10,000 bodies using the different number of threads. The direct algorithm is optimized under single thread condition. You can see it is even faster than using 2 threads. In the visualization, the bodies are displayed as sphere. The sphere model used in this software is icosphere. It is generated by recursively subdividing an icosahedron. An icosahedron is a regular polyhedron with 12 vertices and 20 equilateral triangles. Each triangle of an icosahedron is divided into 4 equal subtriangles per subdivision. In the first demo, I will show you how to control the perspective. Users can press WASD to move, press arrow keys to rotate. Users can also press these keys with the Shift key or Control key to move faster or slower. The visualizing can be paused and resumed by pressing the Space key. The Escape key is used to stop the visualizing and exit. The second demo shows the simulation of solar system. The size of sun and planets have been scaled for display, and 1 second in visualization equals 30 days in real life. The third demo shows the simulation of 100,000 body problem using Barnes-Hart gravity solver and OC tree collision detector. The last demo is as same as the previous one, but using the merge collision resolver.